Previously, we saw that the Galilean transformation had to be modified into what's called the Lorentz transformation. And since we know that length is not invariant under the Lorentz transformation, it's useful to ask, is there anything that is? And it turns out there is. But first, let's just work by analogy to that length invariant with the Galilean transformation. So in the Galilean transformation, we could say have two observers who had coordinate systems that were rotated with respect to each other. So, for instance, let's say this is observer S is X and Y axis, and then we could conceivably have this being observer S primes X prime and Y prime axis. If we were to measure the length of some object, what we would do in relativistic language is define two simultaneous events that occur at opposite ends of the thing that we want to measure. We'll call this event 1 and this event 2. And we would say that the distance between them was d, and from the Pythagorean theorem, we could say that d squared was, well, our observer S would measure this coordinate here to be x2, this to be x1, y1, and y2 like that. So they would say x2 minus x1 squared plus y2 minus y1 squared by the Pythagorean theorem. S prime would do the same thing. They would measure their x coordinates, so this would be x1 prime, x2 prime, y1 prime, y2 prime, to get x2 prime minus x1 prime squared plus y2 prime minus y1 prime squared. And although they'll disagree on the values of potentially all four of these coordinates, and they'll disagree on the differences in the x and the differences in the y, they will absolutely agree on what happens if you square them and add them up. They'll agree that it's still d squared because the Pythagorean theorem is still true. So under the Lorentz transformation, the corresponding thing just gets cleverly called the relativistic invariant. In analogy to this d squared, a very common notation, although by no means the only one, is to call it s squared. And this is equal to c delta t squared minus delta x squared. And if you got y and z axes, you'd then say minus delta y squared and minus delta z squared if you needed it. This is the most common way to define it, although there are authors who define it with the signs flipped. Anyway, under this most usual way of defining it, if the invariant is a positive number, and don't let it throw you that it's squared, it can be negative, it's okay. But if it's a positive number, then it means that this delta t term, after we multiply it by the speed of light, is bigger than our space terms. And so this means that our two events have what's called a time-like separation. And if it's equal to 0, where these two are exactly equal, we call that a light-like. separation, because this basically can only happen with things that involve light or anything that travels at the speed of light, like gravity or something. In either of these cases, it's possible to have a cause and effect relationship. In other words, if event 1 happens before event 2 in one frame, all observers will agree that event 1 happened before event 2. So then that would mean that it would be possible for event 1 to cause event 2. If the difference is negative, then that means that even that light can't possibly travel between the two events, and so we call this a space-like separation. And this means that it's impossible to have a cause and effect relationship. All right. So what would be the equivalent of this is what's called a Minkowski diagram. Because if you look at this looks vaguely Pythagorean theorem-y, except for the fact that there's this minus sign issue. And so because it does look Pythagorean theorem-ish, it does mean that it's not quite correct to think of space and time as being separate things. Instead, we have to talk about space-time. And time is one dimension that is perpendicular to the others. However, it is not a Euclidean geometry. It's what's called a Minkowski space. And so that kind of geometry gets really weird. To help visualize it, physicists will use things called Minkowski diagrams or world line diagrams. And pretty much universally in these diagrams, we put time on the vertical axis and usually just write one of the spatial dimensions, say x, on the horizontal axis. But we kind of keep in mind that this is like all three of them together somehow. So now this would be what S would have. S prime's coordinate system, so if S prime is moving with respect to S, it's going to look something like this. This would be, say, their X prime axis. Okay, that's all good. And then this would be their time axis, like this. And the thing is that it's still perpendicular. Even though it totally does not look perpendicular when we draw it, it is perpendicular. The problem is we're trying to represent something that does not follow Euclidean geometry on a flat video screen that absolutely does follow Euclidean geometry. So you're kind of stuck there. These two are both perpendicular. We just literally are incapable of drawing it that way in the space that we occupy. But anyway, in our example of having, say, a time-like separation, this would, say, be event 1, and this would be event 2 here. And so you would go ahead and read, this is X1, this is CT1, and then here you would have to be very careful doing this. You go down parallel to the T prime axis like this. This would be my X1 prime. I have to go parallel to the X prime axis here to get my CT prime. And sorry, that should just be without a prime there. And that's a 1. And that's a 1. Now, in these diagrams, we always multiply the time by the speed of light. This is so that we can meaningfully draw them in the same diagram. Since everyone agrees on the speed of light, we could just as easily talk about meters of time. Take the seconds of time you have, multiply by the speed of light, and you get meters. In this case, that's convenient to do. Before you think that's weird, we express distances in terms of time all the time. Not just, say, the light years that you hear astronomers use, where they talk about distance in terms of how many years it'll take light to travel, like Proxima Centauri is 4.3 light years away. Means it takes light 4.3 years to get there. Well, you can get how many meters that is by times it by the speed of light, 3 times 10 to the 8 meters per second. And similarly, we also will say things like, oh yeah, that town's 3 hours down the road. Well, you're really expressing a distance. You're saying if you were to get in the car and operate your vehicle at posted speed limits, you would get, in normal driving conditions, you would get to that other town in 3 hours. Well, you can convert that to kilometers or miles or whatever by multiplying the time it takes to travel by the speed limit to get the distance. So we express distance in terms of time all the time, so there's absolutely no reason why we can't express time in terms of distance. So here, the main deal is that with this event, no matter what happens, everybody will agree that this event happened before that event. And that's because you can see it's below here on this axis, and if I go parallel here, we can see that this is below here on this axis. As S prime approaches the speed of light with respect to S, these two axes will approach each other along the 45-degree line in these diagrams. So, just to get rid of a bit of clutter here, let's just focus on event separation to S and think about our intervals. So if we put our first event on the origin, we can draw a thing called a light cone, which is just drawing the 45-degree lines here. And it's called a cone because if you are doing this in more than one dimension, this is going to spin out to be a cone. So this structure gets called a light cone. Now, if I have an event that is inside the light cone like this is a time-like separation. This means that if I boost to anybody's frame, they will agree that this event will happen after this event. There we go. If I have an event sitting right on the light cone, that's when we have a light-like separation between events. And this still means that we can have cause and effect happening between them. Now, where we will disagree on the order of events is if, say, we have an event like this one here that's sitting outside the light cone. This is what's called a space-like separation. Now here, some other observer boosting to a different frame could very well have this event happen before the other event, or after the other event, or at the same time as the other event. But that's okay, because there's no possible way they can have cause and effect relationship. This is because if I emit a pulse of light here, at this moment here, the light will travel out into the future along this light cone here. So this part gets known as the future the future light cone. And then anything in this light cone could have caused this event to happen in its past. But here, there's no way for information about this event to get to this one. For that to happen, information about this event would have had to travel at faster than the speed of light to this location here. And that just ain't possible, as we'll see. All right. So we'll come back to invariance in a bit when we do momentum and energy, but let's go ahead and start thinking about relativistic momentum. So as an thought experiment here, we can think back to one of those problems that we would have done back in mechanics, where say you had two identical massed ice skaters on a frozen pond and they push off of each other. Here what I'm going to do is imagine having a massless spring and 2 point masses m. So if I calculate the momentum of this system before, the x-component momentum is 0. Cool. Now, afterwards, we'll just ignore our massless spring. This mass is going to be going off to the left at minus ux, and this one will be going off to the right at plus ux, like that. So we can calculate the momentum afterwards. Px here is going to be m times minus ux plus m times ux. That gives us 0. So yay, momentum is conserved. Now, will S prime say that momentum is conserved? In the Galilean transformation, they totally would have, but now we run into a problem. Because if we do this, let's just go to a frame where we are moving to into a frame where S prime is moving to the, seeing everything move to the left at uxi prime. There we go. So they would see the here, let's get the spacing better. So uxi prime. Draw my two masses again. There we go. So now they would say the momentum is equal to minus 2 mv. Well, that's cool. Now, I chose this to be this because afterwards this happens to be the frame where this one is going at 0. And so if we figure out what this one is going at, well, that's no problem. We can just velocity transform this. So we get that this one will be u prime is minus 2v over 1 plus v squared over c squared. So we're picking the frame where this is initially seen as going as fast as that is, as fast as this one was before, but in a way to make it seem like it's stationary. So anyway, we figure out the total momentum. It's minus 2 mv over 1 plus v squared over c squared. And that's a problem because they're not equal. They're very, in any real world kind of problem where things are going slow compared to the speed of light, they'd be very close. But they aren't equal. The thing is we know that momentum is indeed conserved. So what must be the case is that our definition of momentum being the mass times the velocity is what's in error. And that turns out to be correct. Einstein was able to show that you can get momentum conservation to work all the time if you properly define momentum to be the mass times the velocity. And remember, we're using u for the velocity of the thing here, over 1 minus u squared over c squared. Now this expression looks so much like gamma that what physicists do is they write gamma mu. But this isn't the same gamma. The gamma we had before was the v, which was the velocity of s prime with respect to s. Here you're inserting u into the expression, which is the velocity that some observer measures. Now, there's basically no confusion here because it's always clear from context which one you mean, with the exception of one particular class of problems where they both show up at once. That's beyond the scope of this treatment here. And in that case, what people will do is they'll write gamma sub u and gamma sub v to keep them straight. All right, so if momentum is had to be redefined, then what does that mean for energy? Well, we can start to do the work energy theorem on this. So we remember that the kinetic energy on some object is equal to the work that some force applies on it from rest, or I should say the net force applies on it from rest. So we'll just say we'll integrate this from u equals 0 to our final velocity u, f with respect to ds. So we'll just assume we're doing this in one dimension. We're just pushing in the direction the thing is going. Now we have to be super careful here. We can't write f equals ma, because that turns out that that version of Newton's second law, as we already saw in mechanics, is not quite right. It's more correct to write that it's dp dt, and in this case here, this is exactly what we need. So we'll say that we are integrating dp dt with respect to s. Now we can go ahead and put in Einstein's revised momentum definition, d dt of gamma mu ds. All right, and we can do a quick bit of calc to say that that's the same difference as integrating with respect to gamma mu ds dt, and observe that that is u. All right, now we're left with this Gacky differential that we have to think about. So let's think about it in parts. So the differential of gamma mu is going to be equal to, well, m is a constant here, so that's at least a small favor. This will be mu d gamma plus gamma m du. Again, I will go ahead and spare the tediousness of it, but we'll have to go in and stick in that gamma is 1 over square root of 1 minus u squared over c squared here and here. Turn the crank on it, and what you eventually get is that this is m times 1 minus u squared over c squared to the negative 3/2 du. So we can substitute that into here for my integral, and I will get that the kinetic energy is equal to the integral from 0 to u du mu 1 minus u squared over c squared to the negative 3/2 du. When you go ahead and evaluate the integral and clean it up, I will just assert that what you get is that the kinetic energy is gamma minus 1 mc squared. All right, well that sure doesn't look a whole heck of a lot like our mv squared from before. 1/2 mv squared from before, so it's probably, or I should say 1/2 mu squared now. So it's probably worth us double checking that. So let's take a look at the case where we are going much less than the speed of light. We should recover 1/2 mu squared somehow from this. So the kinetic energy, putting in for our gamma, this will be 1 over square root of 1 minus u squared over c squared minus 1 mc squared. Now, what you can do is you can go ahead and apply the binomial theorem to this, and you can expand this out. So this term, this will become, and we'll only keep the first two terms. The first term, when we expand this out, is 1. The second term is going to be plus 1/2 u squared over c squared. And then there will be higher order terms, but since we're already saying that u is much less than c, we're just going to go ahead and say that those higher order terms, which goes things like u to the 4 over c to the 4, are basically 0. And then we still have this minus 1 from before, mc squared. So these cancel here, and the c squareds cancel, and what do you know? At low speeds, we do indeed recover 1/2 mu squared. So that's really comforting. Now, let's think about what happens as we approach the speed of light. So if we let u approach the speed of light, we've already seen that this means that gamma is going to approach infinity. And since k is equal to gamma minus 1 times mc squared, when gamma goes to infinity, this is just going to go to infinity. So if we were going to attempt to get an object up to the speed of light, we would literally need an infinite amount of energy, which is more energy than there is in the universe. So, and then we can't even begin to discuss going beyond it if it's going to take infinity just to get to the speed of light. So it turns out that if you're massless, you can only go at the speed of light. And if you have mass, you must always go less than the speed of light. So this means that the speed of light is indeed the speed limit. There you go. Now, getting back to the business with invariants and such, momentum needs to obey the Lorentz transformation. So part of what I deleted in this, what I didn't mention so far, is that yes, we had to redefine momentum like this. But it turns out that in order to get the Lorentz transformation to work, so for momentum to obey the Lorentz transformation, we have to ascribe a time-like part of momentum. Because remember, since we're talking about a unified space-time, we've said that an event is x, y, z, t. So, all right, we got px, py, pz, but what acts like as the time-like part of momentum? So we need a time-like part of momentum. And it was shown that it needs to be the energy of the particle over c, where the energy of the particle is gamma mc squared. So this is the total mechanical energy of the particle. So that's interesting. The kinetic energy, so this is seemingly a contradiction. We got that the kinetic energy was gamma minus 1 mc squared. And however, if the Lorentz transformation is going to work and not break, we need the total mechanical energy of our particle to be gamma mc squared. Now, just like we saw before with potential energy, it was okay to add and subtract constants of potential energy. That turns out to be the case here. We can go ahead and say that the total mechanical energy, gamma mc squared, will be the kinetic energy plus, will be the kinetic energy plus whatever the energy of the particle is when it's at rest. This is just our constant. Because if I put in u equals 0, gamma is equal to 1, and that means the kinetic energy is 0. So just following that thought through, gamma minus 1 mc squared plus E naught. This means that the energy that a particle has when it's at rest is equal to mc squared. And this is what we call the rest energy of the particle. Now, what does that mean? Well, we can actually make matter. And it turns out that you need, if you want to make this much mass, you need that much energy to make that much mass. So quite literally, the interpretation winds up being that this is just literally how hard you have to work to make a particle. Now, it turns out that for momentum, there is also an invariant that both S and S prime will agree on. And it turns out that that invariant is indeed the rest energy. Well, technically the rest energy squared. So no matter what someone measures for the mechanical energy of the particle and the momentum, they always agree that E squared minus PC quantity squared is equal to the square of the rest energy of the particle. This is part of why it is that when you ask physicists today, how do they define the mass of a particle, they'll always just say that it's the rest mass. And there's a couple of reasons for that. Most of our definitions of mass involve the particle being at rest. There's one definition that does not, but most of them do. That's because, you put it on a scale and just sits there, right? It's at rest. So that's very sensible when you're trying to compare things. When this whole business was first coming up, some people did decide to embrace a definition of mass due to the American physicist Richard Feynman, called the Feynman Recoil definition of mass. And in that definition, you were allowed to then bury the gamma here into the m. So they would, in that definition, you'd say the mass was what we would say is gamma m. So if you find books that were written about a generation, well, over a generation ago at this point, there's about a 20-year window where people were particularly enamored with that definition. And so if you've heard things like you can't go faster than the speed of light because the mass of it will go to infinity, that's not how we would interpret that today. That is making a reference to this Feynman recoil definition of mass, which, although it isn't wrong, it's a definition. It turns out to be a definition that isn't as useful. So physicists will say, no, the mass of the thing doesn't change because the only way I know what the mass of the thing is put on a scale. When it's sitting on the scale, it isn't moving. So we can only meaningfully talk about rest masses. And so whenever we write a mass, we mean the rest mass now. But it turns out that a lot of the mass of any particle we look at is actually coming from the strength of the interactions that are holding the constituent particles together. So just let me give an example of this. So the process that occurs in the core of the sun that eventually causes light to make its way to the Earth is a thing called the proton-proton chain. There's other processes that occur, but this is the single biggest one. So it's a 3-step nuclear process. In the first step, lone protons, so I'm going to write them as hydrogen 1 nuclei. Every so often, they will be just happening from the heat and the pressure to be going fast enough and by just sheer random chance approach each other straight on enough that they get to within about 10 to the negative 15 meters of each other. So as they've been approaching, they are feeling massive electric repulsion, but if they get to within 10 to the negative 15 meters or so of each other, then another force of nature called the strong nuclear force kicks in. It turns out that this force is a short-range force, and if you're outside that distance, it doesn't do anything at all. But once the strong nuclear force kicks in, it will attract the 2 protons together. Now, 2 protons being bound to each other are not stable. And so what will happen is immediately one of those protons decays into a neutron. And so this gives us a hydrogen 2 isotope. So this is also known as deuterium. Now there are a couple of decay products that fly out when the proton, via the weak nuclear force, turns into a neutron. It ejects a particle called a positron, which is an electron, except it's positively charged. So it's not the same thing as a proton. It's an electron that's positively charged. And then it kicks out an electrically neutral particle that has almost but not quite zero mass, called a neutrino. And there are 3 flavors of these neutrinos, and this particular one gets called an electron neutrino. All right. So what winds up happening, and then let me just finish off the other 2, and then we'll focus just on this piece of the process. In the next piece of the process, another proton eventually happens to find one of the deuterons that we've made. And again, they get into close enough range so that the strong nuclear force can take over, and they just get sucked together into something that has 2 protons and 3 electrons. This is a helium-3 nucleus. It turns out that the exact way they come together in an excited state. So we write a star to note the excited state. It goes from this higher nuclear energy state to a lower nuclear energy state. And emits a photon to get rid of the extra energy. Then the last step of the proton-proton chain, and yes, there is an alternate pathway, but I really don't want to get into it. The one that occurs most of the time will be that 2 of these helium-3 nuclei will fuse. And what will wind up happening is, it turns out helium-6 is not stable. It turns out that a structure with 4 protons and 6 neutrons is four protons and 2 neutrons is not stable. 2 of the protons managed to escape because the electric force was strong enough to let that happen. So you end up with a helium-4 nucleus, which is the most common form of helium, and then 2 protons leave the party. Although they're still floating around in the sun somewhere, so they could wind up going in. So if you count everything up, for every one of these steps, these 2 steps have to run twice. So the net result is that you get 4 protons eventually joining together to become 1 helium nucleus, 2 positrons, 2 neutrinos, and 2 photons, and the whole process was catalyzed by 2 other protons. So anyway, it turns out that the heat that we get from the sun is basically coming from these little bits of debris, like the positron, the neutrino, the photon here. Okay, the neutrino just flies right out of the sun because it basically doesn't interact with anything. But the positron and the neutrino, they carry off a lot of what turns out to be the excess energy that's coming out of this interaction. And we'll get to a second where the energy is coming from. That heats up the sun, and then eventually that heat works its way to the surface of the sun and is emitted as radiation, making light. And 8 minutes later, that light gets to the Earth, strikes winds up hitting on some farm, and grows a Pop-Tart. Alrighty, so let's just focus on this first reaction. All the others have a similar story, but let's just focus on this reaction right here. It turns out that if you add up the mass of the products, it's less than the mass of the reactants. Now, I know that you're probably saying, wait a minute, my chem instructors have always told me that matter can neither be created nor destroyed. That's not quite right. It turns out that mass is not a conserved quantity even in a chemical reaction. It's just that in chemical reactions, we'll see that the differences in mass are so small that they can't be measured by any practical device. So that's why chemists can get away with saying that. But in nuclear physics, where the energies involved are higher, we actually do have to worry about it. So where's that energy coming from? Well, it's because this is a less stable state from the perspective of the strong nuclear force than this is. The 2 objects wanted to be next to each other. So the strong nuclear potential energy decreased. So that energy had to go somewhere, and it went into these decay products here as kinetic energy and ultimately as heat. So let's just calculate how much the rest energy of the system changed by. So the change in the rest energy, delta mc squared. All right, that is going to be, we've got the mass of a deuteron, c squared. That's its rest energy. This is the rest energy of an electron. This is the rest energy of a neutrino. Now, although the mass of a neutrino isn't 0, it is so close to 0 compared to basically any other particle in nature. I'm just going to make that go to 0 right now. And then we have to subtract 2 times the rest energy of 1 proton. All right, now to do this, I am going to have to very, carefully take the masses into account. So if you look it up carefully, the mass of a deuteron is 2.014102 atomic mass units. And this is an atomic mass unit, and so just converting from atomic mass units to MeV over c squareds, we'll put one atomic mass unit in the denominator. An atomic mass unit in MeV over c squareds, remember that's a unit of mass that we already saw. It's 931.494013 mega electron volts over the speed of light squared. And then we're timesing the whole thing by the speed of light squared. So the atomic mass units cancel and the c squareds cancel to give me MeVs. The mass of our electron is 0.511 MeV over c squared, and again we're timesing that by c squared, so we can just cancel the c squareds. All right, like I said, we're ignoring the neutrinos, so then we will subtract 2 times the mass of a single proton is 1.007825 atomic mass units. And again, converting, that's 931.494013 mega electron volts per c squared per atomic mass unit. Then we're taking the whole thing and timesing that by c squared. So the atomic mass units cancel and the c squareds cancel. And when it's all said and done, this is minus 0.931 million electron volts. So this means that the rest energy of the products in this first step of the proton-proton chain are the better part of 1 billion eV per c squared lighter than the 2 protons that made them up. This energy comes from the fact that we are now in a lower strong nuclear energy, potential energy state, combined with, since the weak nuclear force was involved, a lower weak nuclear potential energy state. So it turns out that a lot of the mass of particles that you see is actually from the binding energy of the forces that are holding the constituent particles together. Now, the same sort of thing happens in a chemical reaction. But the thing is, in a chemical reaction, the change in the energy of the system before or after is just EVs, not like a billion EV. And so the fact that these changes are, or even like tenths of EVs, are like a billionth to a 10 billionth as strong as you would see in a nuclear reaction, and we're already having to keep very careful track of our decimal places with a nuclear reaction. There just literally isn't any device that can measure the mass change in a chemical process. But if the process is, if a chemical process is exothermic, you will get that the object does indeed have its mass drop because of the change in the binding energies. As a fun example, if you take an electric car that, say, has an 85 kilowatt hour battery pack and you drive it to depletion, it'll turn out that the mass of the car dropped by about the mass of a hydrogen atom or so. So, these are not very large changes when you're doing this over chemical scales. But on nuclear scales, it really shows up. So with this, I think it's time to go full circle and revisit that same electron gun problem we did all the way back at the beginning when we started relativity. So here's our electron gun. And again, we will have the filament that's boiling, that's causing electrons to come off. We'll say that this is our negative plate here, and this is our, whoops, we need a little hole in our positive plate here. And once again, we will just turn the dial to set the voltage difference of this to be 1.022 times 10 to the 6 volts. Now, electrons will come off of the filament and be accelerated through this potential difference. So once most of them will just collide with the positive plate, but occasionally some will fly through the little hole. So when they do, what's their final speed? Well, we can go ahead and conserve energy here, just like we did before. We'll just say that our final kinetic energy is equal to our initial potential energy. Our initial potential energy is equal to E delta V. But now instead of writing 1/2 mv squared, we know better, and we know that we have to write gamma minus 1 mc squared. Now, gamma contains our U within it. So the steps here is just like before, your knee-jerk instinct is to calculate beta and then calculate gamma. Here we're going to calculate gamma to get beta and then say, oh, our final speed is beta times the speed of light. So let's go ahead and do that. So we'll first go ahead and just solve this for gamma. So dividing through by mc squared, we'll get gamma minus 1 equals E delta V over mc squared, or gamma is equal to 1 plus E delta V over mc squared. All right, so let's go ahead and figure that out. That's going to be 1 plus, we can just leave our E because that's the beauty of using EVs for units. We set the potential difference to be 1.022 times 10 to the 6th volts. The mass of an electron is 0.511 times 10 to the 6th EV per c squared. And then we're going to take that and times it by c squared. All right, so the c squareds there cancel. This E and that E cancel, and the volts cancel. And then this is exactly 2 times that, which is why I picked the number to be that. And 1 plus 2 is 3. So we get that gamma is 3. All right, so now we remember that gamma is 1 over root 1 minus beta squared. We know that that's equal to 3. So we can square both sides. 1 over 1 minus beta squared is equal to 9. We can do a little flip-flop action here, cross-multiply action to get that 1 minus beta squared is a 9th. So beta squared will be 1 minus 1/9, which is 8/9. So that means that beta will be the square root of 8/9. And if you want to make that pretty, that is 2 root 2 over 3. So this means finally that our final speed, U, is equal to beta times the speed of light. So it's 2 root 2 over 3 times the speed of light, which is 0.943 times the speed of light, which is indeed in agreement with experiment. All right, I hope you've enjoyed this little trip through relativity. We'll catch you in the next set of videos. See ya.